Okay, we are going to go through the conclusion and what to put in there for your Boom Goes the Dynamite lab. From lab, we ended up with a relationship of inverse between the velocity ratios and the mass ratios. And to linearize that, then we just regraphed. Still the same y-axis, but now we inverted our x-axis. And so we ended up with now m2 over m1, and that straightened it out. Ideally, we would have got a slope of 1, and it's unitless because the units cancel out by taking the ratios. So besides this, the general overview, what do we need to have in there? I kind of have a play-by-play of what I'm looking for in the conclusion. So we got about 11 different points that we're looking for, and I'm going to kind of bring these up and show you individually what we're thinking. The first thing, state research question. You want to bring people into the paper by saying the purpose of this lab is to look at the relationship between the velocity ratio and mass ratios for two carts exploding. After you say that, it's good to just then go right into what a definition of explosion is in physics. And if you remember from our discussion, pretty much anything that just starts as one and separates into two or more would be considered an explosion. After that, you're going to address your hypothesis. Remember to say that you either support or reject your hypothesis because of the data that was shown. If you thought it was going to be quadratic, but it was inverse, you would say, my data rejects my hypothesis. Don't say that you were wrong. If you thought it was going to be inverse and you were right, don't say that I was right. Just say, my data supports an inverse relationship. Moving on, number 4, why was it okay to look at the displacement ratio to get to the velocity ratio? Here we're going to be talking about how we kept the time consistent. You remember we hit the carts to hit the back wall at the same time, and what that did was give us a means of canceling out time in both sides of that ratio. So we were technically looking at displacements, but it was also the same ratio that would show up for velocity. Number 5, how'd you linearize? So we just want you to mention, because the graph was inverse, we had to take 1 over the x-axis. And you can get into a little bit more of like your fraction was m1 over m2, so by taking 1 over that, that just flips it into m2 over m1. The reason that's important is because then when the final formula shows up, that's what gives us mv of one car equal to mv of the other car. Number 6, what does having a slope of 1 mean? So basically talk about the fact that it's 1, that would just mean the y-axis is exactly equal to the x-axis. And then we will get into the next part. So why no units? We ended up with ratios, and when you divide a meter by a meter, that's going to cancel out. So we don't have any units in our math. And how did your carts display the conservation of momentum? You can get into that with describing how the heavier cart would move slower so that the total momentum was conserved, or the lighter car moved faster. Number 9, formula from your linear graph. Make sure to go into, let me show you that a little bit here. The formula, we had V1 over V2 equaling 1 times M2 over M1. And so equation-wise, when we cross-multiply that, all that says is that this ratio of velocities equals this ratio of masses, the inverse of the masses. So we cross-multiplied and divided out, and we got m1 v1 equal to m2 v2. So you want to give that whole thing. We started with this. If you think about it, this was the math model of your graph, and then this was the derived formula that we got from the math model. So give both of those, or show how to go from one to the other in your conclusion. Other examples, you can think of just a couple other examples of explosions and how you've seen conservation of momentum, and then sources of error. This is going to be important. There was a lot of error in this lab. Not a whole lot of people got exactly 1, so I want you to talk to me about why that was. What kinds of things led to that error. One thing in particular, I'll kind of sketch out a track here. We had these backstops, and if you imagine 2 carts on the backstops after they exploded apart, well, the distance that you measured from the starting point. Did you go to exactly where the front of the car was? Did you measure all the way to the back of the car? Depending on which lab group you were in, you might have measured differently, and that could have had an impact. Also, the mass ratios would have something to do with this too. We saw that even though they're supposed to be 250 grams, some of them were about 259 grams, some of them were 252 grams. So there was possibly a difference in your mass ratios between one cart and the other. And if you put that in your data set, that's going to start messing with your one-to-one ratio. It's not truly a one-to-one if these two numbers were different. So there's some other things in there as far as skipping and sliding on the track. Maybe the springs weren't firing consistently every time. There's all those kinds of things I want you to talk about and brainstorm and put in there. Sources of error should not just say human error. We got to have specific things that could have led to the data being off. So try to give at least 3 to 4 good sources of error. That's it. Conclusions due Monday. Have a good weekend.